Hello, my group consists of Juan Pablo Fonseca Celis, Johan Sebastián Poza Beltrán, Iván David Giraldo Garavito, David Fernando González Soler, and Michael Steven Fonseca Muñoz. This is the differential equations study, taught by Diego at the University of Cundinamarca. What do differential equations study? Differential equations study problems that represent the real world in motion. For example, they can involve problems related to velocity and position, population issues, temperature issues, and many other problems of the real life. What does it mean to model change? When we refer to modeling change, we want to make reference to tell a situation in which a situation is changing with the passage of time. We are going to model or structure it in a mathematical way. It is a way in which we can predict or get closer to a real value of that situation in t time. What is a dynamic system? A dynamic system describes how the state of physical, biological, or economic systems change. This is achieved from rules or equations that govern how its state variable change at each instant. They also reveal qualitative properties. If it is stable or tends to get out of control, if it repeats patterns periodically, if small changes lead to completely different behaviors, but with no bifurcations, or even if it enters a chaotic behavior, where the system is unpredictable in the long term despite following defined rules. What is a state variable? A state variable is a quantity that, depending on the context in which it is being applied, is represented with certain symbols to correctly indicate what it is measuring. What makes these quantities special is that they contain all the necessary information to know how the system is going to behave in the future. These quantities can vary with respect to time. What is the temporal evolution? Continuing with the previous idea, to complement temporal evolution in a dynamic system means the change that state variables experience with the passage of the time. This is because these variables do not always remain constant, nor do they follow the same trajectory, but rather they respond to the inputs of the systems and to its own internal dynamics. Relation with ODEs. Dynamic systems and ordinary differential equations are closely related, and that is because ODEs are precisely the mathematical tool that is used to describe how the state variables of a dynamic system evolve with the passage of time. That is to say, when we want to express mathematically, we do it through ordinary differential equations. So, one would not make much sense without the other. What is an ordinary differential equation? An ordinary differential equation is an equation that involves a single unknown function of a single variable and a finite number of its derivatives, so that the relationship contains the independent variable, the function, and its derivatives. The order of an ODE is the order of the highest ranking derivative that appears in the equation. In ordinary differential equations, we find two types of variables, the dependent and independent ones. As their name indicates, the dependent variables are those that depend on the other to take a certain course. Meanwhile, the independent variables are those that do not depend on another to take a value. The easiest way in which this can be seen applied is in problems that include time, since it is the most common example. Time acts as an independent variable because, putting it in logical terms, we are never going to be able to control time, so it takes its values on its own. The independent variable changes according to the problem. On the other hand, y is the independent variable since its value depends on the independent variable. A basic example of an ordinary differential equation is dy by dx equal y. It is ordinary due to the fact that it relates a single function with a single independent variable, which in this case is x. The order of this ODE is first order, due to the fact that the highest order derivative that appears in the equation is the first derivative. Now then, the solution to these equations is y equal to c Euler power to x, where c is a constant that is going to depend on the initial conditions of the problem. This means that once we know those conditions, we can determine exactly how the function behaves.
Alright, hypothetically speaking, you have just engineered a virus, nothing personal, just science. One infected person and out there 8 billion potential victims, completely unaware. So the real question is, does your virus take over the world or does it just, fizzle out quietly embarrassingly? Turns out that's not absolute. It comes down to a single number, and that number comes from a differential equation. This is the math that decides if your virus wins. Okay, the real world is messy. People travel, hospital exists, some people are immune. Forget all of that. We're going to build a simpler world. A world with only three types of people. First, the susceptible. They are healthy, they have no idea what's coming. In our model, we'll call them S. Then, the infected. That's your virus at work. They carry it, they spread it. We call them I. And finally, they removed. They either recover and can get sick again, or they didn't make it. Either way, they are out of the game. We call them error. And well, in this world, people only move in one direction. You start susceptible, you might become infected, and eventually you end up removed, not going back. This is simple and brutal and quite surprisingly accurate for our purposes. So, we have our three groups, but here's the real question. How fast does the infection actually grow? Let's think about it. Don't memorize anything. Just think. If there are more infected people or there are more cars walking around, does the virus spread faster or slower? Faster, obviously. So the rate of new infections grows with the number of infected. Let's write that. But infected people need someone to infect. If everyone is already sick, there is nobody alive to catch it. So the spread also depends on how many susceptible people are still out there. More infected, more susceptible, multiply them, that's your transmission. Now, infected people don't stay infected forever, they recover, they leave the group, remember? The faster they recover, the faster I shrinks. So we subtract that. Gamma is just the recovery rate. High gamma, people recover faster. Low gamma, they stay sick longer. And that's it. That's the whole story of the infected group, written in one line. On the left side, di over dt is just asking how fast is the infected group changing right now. The right side gives the answer. Two forces, one pushing up and one pulling down. Your virus wins when the pushing beats the pulling. We have our equation, but here's the honest truth. This system has no clean solution. You can just integrate it and get a neat solution. The three variables are all tangled together. But we don't need a formula. We need to ask a different question. Instead of asking where does the system end up, let's ask at any given point which way is it moving? Think of it like wind. You don't need to know where every air particle will be in an hour. You just need to know right now which way is it blowing. And my little dark scientist, that's exactly what a directional file does. Our world has two moving parts, S and I. Error just follows. So let's put S on one axis, I on the other. Every point on this plane is a possible state of our epidemic. And at every single point, our equation tells us exactly which way the system is moving. We draw that as an arrow. Now, you see this little y dot, that is our starting point. One infected person, almost everyone susceptible. And watch. The system follows the arrows. The file, it has no choice. Okay, we have already seen the threshold line. That's exactly the point where the epidemic tips, where infections stop winning and start losing. Ask a different question. What happened at the very beginning, when the virus is brand new, when almost nobody is infected yet? But at that moment, S is basically 1, the entire population is susceptible. Let's modify our original equation into this way, which means everything depends on the sign of the thing beta minus gamma. If beta is bigger than gamma, the infection grows. If gamma is bigger, it dies instantly on day 1. So let's write that more cleanly. Take beta and divide it by gamma. Cut that number error not. And with that, we can make a little change in our equation. R not greater than 1, your virus wins the opening move. R0 less than 1, it never gets started. So R0 is simple. How many people does one infected person infect before they recover? One person, one number. That's the whole game. Watch what happens when we move it. Same equation, same structure, one number change, and the entire personality of the system flipped. That's not a coincidence. R naught is the skeleton key. Every epidemic that has ever existed has an R naught. Different diseases, different worlds, same question about R0. The epidemic peaks exactly when the remaining susceptible population drop below that threshold. R0 isn't just a formula, it's the moment where mathematics earned its keep. There is no closed form solution to the zero equation. You cannot write a clean formula, not tidy expression gives you I of t. The system is coupled, non-linear, it refuses to be solved the polite way. So we do something more honest. We let a machine trace the path step by step. This is numerical integration, not an approximation, not a sheet. The same logic the universe uses, given where you are now and the direction of change, find where you'll be next. And with the little trick we've got, the susceptible population, it falls slowly at first, then fast, then it's low again. It never reaches zero. Red, the infected, it rises, it peaks, it falls. That shape, that arc, it is the entire story of an epidemic in one single curve. Green, recovered. It climbs as the other resolve, quietly, inevitably. Three curves, one moment matter more than the others. Here, the peak of I, this is the worst day for the better, as you can see, the moment where the healthcare system feels it most. But look what happens just before the peak. The susceptible population crosses a threshold, the same line we found in the directional file. And eventually here, I reaches zero, not because the virus ran out of victims, because the remaining susceptible fell below the critical threshold, the fire ran out of fuel it could reach. Now, watch what R0 does to all of this. SIP model works, we've seen, but it made promises it can't keep. Let's look at what it assumed, quietly. First assumption, the population is closed. Nobody is born during the epidemic. Nobody dies from anything else. Second assumption, recovery is permanent. Once you leave I and enter air, you stay, no reinfection. Third, beta is constant. The transmission rate never changes. No season, no lockdowns, no behavior change. People spread the virus at the same rate on day 1 as on the day 204. There is no space, no network. Everybody is equally likely to infect everyone else. A farmer in Montana and a subway community in Tokyo live in the same imaginary zone. These aren't minor technical complaints. Each one is a door. Will the first one open? At births and deaths. And S, the refill, the epidemic becomes endemic. It never fully leaves. The second, let air flow back to S, and you get reinfection models, wave after wave. Make beta a function of time, and suddenly interventions work. A lockdown is just beta dropping. A suppressed birth event is beta speaking. At an exposed class, people infected would not get infections, and the seed model becomes safer. The incubation period enters the model. The curve shifts in time. Each crack is not a failure, it's a coordinate. It tells you exactly where the next equation lives. The same language, more words. Here was the first weapon, just these are the others. We started with a question. One infected person, 8 billion potential victims. Does your virus win or silently die? Now, you know the answer it's a look. It is a number, one dimensionless number that decides everything, where the arrows in the file point up or down, where the curve rises or collapses, where the epidemic earns its name. R naught equals beta over gamma. But here's what I didn't tell you at the start. R naught is not fixed. Beta can be engineered, how easily the virus binds, how long it survives on surfaces, how silently it spreads before the symptoms appear. Push beta up, pull gamma down, watch R0 climb. And we've only been working with the simplest model. The real models are darker. They have incubation periods, hosts who spread before they know they are sick. They have network structure, super spreads who touch 1,000 people while others touch there. They've got waiting immunity, a record population that slowly forgets. Each feature is a lever. Each lever moves R0. You engineered a virus. You choose beta, you choose gamma, you choose the incubation window, the transmission network, the immune escape. So let me ask the question again, the one from the beginning. Does your virus win?